Thank you all for joining us today. Today's webinar is Credible P50 to P90, Raising the Bar for Bankable Energy Yield Assessments. We will be showcasing our integration with PowerUQ that offers Monte Carlo uncertainty analysis for bankable solar energy reports. So for today's agenda, we'll give you quick intros on Terabase and PowerUQ, talk about the summer of bankability, showcase the PowerUQ extension that's built into PlantPredict with an overview and demo. From there, we'll discuss the real-world impact of PowerUQ's uncertainty analysis, talk about pricing and special offers, and finally go into 15 minutes of Q&A to close out the session. Our presenters today are David, Director of Sales for PlantPredict at Terabase, and Chetan, Co-founder and CEO of PowerUQ. And with that, I will hand it over to David.
Yeah, I'm going to turn off my camera so you guys can focus on the presentation. Thank you, Isaac, for the intro. For those of you who are new to Terabase, we have multiple product lines, but our overall mission is to reduce the cost and accelerate the deployment of solar through software and automation. First on the left, you see PlantPredict. That's the product that I'm responsible for. It's our solar modeling engine. And in the middle, we have our construction management software and also our automation platform called Terafab, which is installed in industry-leading 100 megawatts to date. And it's set to install hundreds more in 2026, as we just recently released our version 2 of that hardware, and we're really excited about that. On the right side, we have our SCADA, plant controls, and performance offerings, which integrate seamlessly into PlantPredict for expected energy. So you can see we have products that cover the entire value chain of a utility scale solar power plant. Okay, moving on. Now that you know a bit about who we are and what we do, and before we get into the PowerUQ integration, I want to take a couple of minutes to share something bigger that we've been working on for a little while now. We're calling it the Summer of Bankability, and here's what that means. For 30 years, 3 full decades, there's been one tool that the financing community trusts when it comes to yield assessments for solar projects. One tool that sits behind virtually every energy model submitted to project finance, and that tool is PV-Syst. Now, I want to be fair. We owe a lot to PV-Syst. It served the industry well, but its dominance was never really a function of being the best available option. It became the standard before anyone had a credible alternative, and the standard stuck. For 30 years, the financing community had no reason to look elsewhere, and so they didn't. That changes this summer. This summer, PlantPredict V12 is going to be the tool that the financing community starts to accept and eventually starts to expect. Energy yield models generated by PlantPredict are going to become the bankable standard, and we're confident of that. We're publishing 3 IE independent validation studies that provide rigorous third-party evidence that V12 can be trusted. We've already had direct conversations with banks and financial institutions, and they've indicated that they're open to accepting PlantPredict generated yield models. The door is open. This is the summer we walk through it. Go ahead, Isaac. So why is PlantPredict the right tool to break the monopoly? Let's walk you through what PlantPredict does that PV-Syst simply cannot match, especially for utility scale solar. Let's start with the fundamentals. Our physics-based engine uses modern algorithms and up-to-date defaults. We're not maintaining code that was written before most of our customers graduated high school. And unlike PV-Syst, PlantPredict is fully cloud-based. It runs directly in your browser, no installation required, and it works on any operating system, whether your team is on Windows or Mac. That means everyone is on the same platform, collaborating on the same model in real time. No more emailing project files back and forth. No more which version is this. No more version confusion or new updates to download. Plus, we support sub-hourly modeling. For anyone doing serious analysis on behalf of a sophisticated lender or a technical advisor, this matters. Solar irradiance and system performance don't average out neatly on an hourly basis, and our modeling reflects the actual physics of what's happening on the site. But sub-hourly modeling also unlocks something very important. Your model doesn't have to die when a project reaches commercial operation. You can use PlantPredict to model expected energy on operating power plants. So your energy model lives on from development through construction, all the way into operations. And then there's 3D modeling speed. For utility scale projects, shading analysis has historically been a bottleneck, a genuinely painful part of the modeling workflow. PlantPredict, running on version 12, is significantly faster than anything else available. We use GPU-equipped cloud servers, and we're talking about meaningful time savings on large-scale projects that translate directly into faster deliverable turnaround for your clients and more time to focus on optimizing your plant production. Now, here's the differentiator I want to focus on because it's uniquely illustrated by our co-presenter today. PlantPredict has open REST APIs. That might sound like a technical feature, and it is, but the business implication is profound. PVSys is a closed system. You can import data in and you can export results out, but you cannot programmatically interact with it. You cannot build on it. You cannot extend it. PlantPredict is an open platform built API first, and that means that the entire solar software ecosystem can connect to us, build on us, and deliver new capabilities to our users without us having to build everything ourselves. PowerUQ is the most powerful example of what that enables. They've built a deep production-grade integration directly on top of PlantPredict. Their customers model in PlantPredict. PowerUQ calls our API to run probabilistic uncertainty quantification at scale. And those results feed directly into a bankable report that goes in front of lenders. That entire workflow runs without any manual exports, any copy and paste, any version mismatch. It just works. And PowerUQ is not alone. Our ecosystem of integrated partners is growing, and that means PlantPredict gets more powerful with every new partner that builds on it in a way that a closed source desktop application just cannot. So now that you know what what we're thinking, I know what you're thinking. This sounds compelling, but we've been using PVSys for years. Our clients expect it, and our workflows are built around it. The switching cost sounds real, and you're right. That is a real challenge. We've heard it, and we've designed the transition specifically to lower the barrier at every step. First, getting started is simple. You can register for a user account, and our pricing is right on our website. Full transparency, no sales call required to find out what it costs to get started. Subscriptions start for as little as $150 per month. And we have options for every type of organization, whether you're a boutique independent consultancy running lean or a global IPP with a formal procurement process. You can get started immediately. No lengthy sales cycles, no friction. Second, and this is the one we're genuinely excited about, we are building a PVSys project import tool. The idea is simple. You take projects you've already invested time in and you bring them directly into PlantPredict. No rebuilding from scratch, no lost momentum. We expect to have this available in beta form by PVPMC in May. So if you're attending that conference, keep an eye out for it. Your historical work does not have to stay locked in that legacy tool. And third, we know there's a learning curve with any new tool, and we've invested heavily in making that curve as gentle as possible. We're rolling out a full library of how-to guides, step-by-step video tutorials, and expert documentation over the course of the summer. In fact, we just released our new documentation platform last month. So as the season progresses, you'll have more and more resources at your fingertips. Everything you need in order to get up to speed fast and always have something to turn to when you hit a question. We even have an AI assistant in our documentation platform that'll answer questions for you. The bottom line is this: the financing community is already open. 3 independent validation studies are on the way. The technical case is solid. The transition is manageable. And the cost of not switching is that you remain dependent on a 30-year-old desktop application that was never built for the scale and complexity of the projects you're working on today. Now is the time to future-proof your energy prediction workflow, and we are here to make that transition as easy as possible. And we hope that today's webinar with PowerUQ is one more piece of evidence that PlantPredict is ready to be your platform. That is the end of the opening remarks. Before I hand it over to Chetan, we have our first poll question for you to answer. So Isaac, why don't you go ahead?
Here's our first poll question. Which stakeholders in your organization care about uncertainty analysis? I'll give you a few moments to answer the question. Still see some answers coming in. And okay, I will go ahead and end and share the results. Looks like project finance team came out on top. And I'll pass it over to Chen.
Thanks, David and Isaac, for setting the stage. Hey, folks, I'm Chetan. Uh, Before we dive into all things PowerUQ, I wanted to share a little bit of background that compelled us to work on this challenging but fun problem. This is how a target solar portfolio looks like. We are all striving to achieve the target P50. That's the investor's hurdle rate that we are all doing our jobs to meet, where approximately half the projects, half the time, do better than the target P50, and maybe the rest don't. Next slide. But the realized portfolios have reported shortfalls. Now, this one particular example is from a study published by Wells Fargo a couple of years ago, where the realized P50 was lower than 4% that of the target P50. So the target P50 is where the performance index is 1 of that portfolio. For a little bit of additional nuance, these results are after accounting for availability and curtailment. Now, this difference before accounting for those two things was about 6.5%. So just for some context. Next slide. So why does this happen? The reality is that weather, equipment performance, and the grid, which are all uncertain in their own ways. So weather is variable, equipment performance has model uncertainty, and the grid is also variable and uncertain, interact over the project's lifetime. And these uncertainties not just interact, but they also compound as years roll by for a project. So much like this animation, it leads to infinite number of random walks of these interactions, which the conventional uncertainty methods have proven inadequate to capture, especially for P50. I recently spoke at the ACP Peak conference in Denver on this topic. I'm happy to share the deck if you would like to know more and how these two methods compare. Next slide. That's why we built PowerUQ, a project lifetime uncertainty calculator, suitable not for just the downside cases like P90 and P99, but also to reveal the uncertainty in P50. And now, if that's the first time you've heard that sentence, that P50 has uncertainty, I'm sure you're going to enjoy the demo here in a couple of minutes. PowerUQ can calculate a credible downside for debt sizing or for project finance functions, just like the poll showed, account for the uncertainty in P50 for a robust generation time series for credible IRR calculations, the profitability of the project, distinguish between the model and weather uncertainties because weather averages out, but the model uncertainty can persist as a bias in your estimates. Enable sensitivity analyses to study which factor is driving the uncertainty in generation. This is especially useful when you don't know what the exact uncertainty in that input parameter is. Even if you don't know what the uncertainty input should be, you can always study its relative impact on generation to decide if it's worth doing anything about, if it's worth investing dollars into. And finally, it paves the path to hit the holy grail, which is closing the model loop, learning from performance data to tune the performance and uncertainty models. We have a suite of validation results on how this can be done on real projects to show later in this webinar. Next slide. So let's take a look at who should care about generation uncertainty. In the greenfield stages of a project, it can help with early stage feasibility analyses, uncover hidden risks, guide uncertainty-aware designs. For example, one of our internal case studies showed that a high DC to AC ratio might be a hedge against uncertainties in early years due to the interaction between clipping and degradation. Project term robust P50 forecasts provide a credible IRR basis that you can use for your financial models. In mergers and acquisitions, it can help estimate the residual value that's left in the project so you can price it effectively. For project finance functions, the most prominent use case, which I think most of us are aware of, has been used for financial structuring, such as debt sizing, tax equity sizing, but also for conducting studies for parametric insurance, performance guarantees, and sensitivities for IRR to the risk in the particular project. For EPCs, the ultimate test is passing the capacity test or the performance test, and knowing what the uncertainty in the short amount of data that you have can help you plan better in achieving the right outcomes for you. Asset managers benefit from triaging reality against a credible P50 and also study portfolio effects to see if they're on track, and also help you kind of figure out what projects should be in your portfolio for a long-term steady rate of return. The operations and maintenance functions can use the forecasts ahead for day-ahead forecasts, hourly forecasts, to tune their operating models better based on the uncertainty. With more operating data, you get more accurate. So you can have that rigorous way of doing things in your organization if you are aware of the uncertainty in your estimates. The fact is that uncertainty affects all project stages and all project stakeholders, directly or indirectly. You may know it or you may not. Before we move on to the demo, back to you, Isaac, for the next poll.
So we have a series of questions here, just a two-part question. I'll go ahead and launch the poll now. So what % of your projects do you feel like meet their P50 expectations? I'll allow a few moments for you guys to answer. Okay, and I'm going to wrap up the poll now. Looks like 50% is in the lead there. Less than 25% came in second place. More than 90% came in third. And let's go to our next poll question. I'll go ahead and launch this as well. What % of your projects do you feel like meet their P90 expectations? Again, I'll give you guys some time to get your answers in. All right, going to wrap up the poll. Looks like more than 90% came out on top, and 50% then less than 25%. Okay, and I'll hand it over to David.
All right, thanks, Isaac. Well, I appreciate everybody's honesty in the poll questions. I feel like those were very honest results. Obviously, not everybody had all their projects or 90% of their projects being greater than P90, and not everybody said that more than 50% of their projects were P50. So it was great. All right, I want to talk just for a moment about PVPMC, which is coming up in May, and it's going to be held in Albuquerque, New Mexico. This year's conference is already sold out, but I believe they are still putting people onto a waiting list if you're interested. This is my favorite conference of the year. Terabase has been active in the PVPMC community for many years, so we're happy to be gold sponsors of this conference once again this year. Even if you can't attend, all the presentations will be posted online after the conference has ended, so there's a wealth of knowledge that will be made available. Our guest today, Chetan, will be presenting on why nominal generation is not P50. Surprise, surprise. He will also be hosting a parallel session on day 3 to allow attendees to dig deeper into PowerUQ. My colleague, Jason Spokes, who you guys have probably seen on previous webinars, he's going to be presenting an update on PlantPredict and will be sharing some details about our development roadmap. Our principal performance engineer, Arthur Ono, will also be hosting a parallel session on day 3 to provide some training on how to properly do a 3D model in PlantPredict. If you are not already registered, or if you're already registered and planning on attending, we hope you enjoy our presentations and join us on the day 3 sessions. So now on to poll question number 4.
All right, poll question number 4. So I'm going to launch this now. How do you currently perform uncertainty analysis in your workflow? I'll give you guys some time to answer. All right, I'm going to close this poll. It looks like we have a spreadsheet for that came out on top with offload to IEs following behind that. And I'll go ahead and close that. And let's get ready for the demo.
Thanks, Isaac. That was definitely a very interesting poll, that last one. And I really hope that you folks get a chance to see either my talk from ACP or the one that I'm about to give at PVPMC about the shortcomings of using a spreadsheet for uncertainty analysis. So the workflow of PlantPredict and PowerUQ integration really starts in the PlantPredict interface. So folks who are already PlantPredict users will probably find this familiar. I have this one project, PQ Barstow, which is in Barstow, Southern California, with a low weather variability, and I have a bunch of predictions here that I've done to evaluate it in different ways. So I'm gonna specifically look at this benchmark single axis tracker 101 megawatt project. And once this project is, this prediction is run in the PlantPredict interface, you have access to the energy numbers in PlantPredict. And the next step after that is to go to PowerUQ interface, where you enter your API credentials and connect to PlantPredict. You get to see all your projects in here. I'm going to select the Barstow project and the specific prediction that we just looked at, and load all the details from PlantPredict, such as the design, the first year energy, and so on and so forth. In here, our journey really starts with the weather, which is probably the most important part of uncertainty analysis. You have the option of bringing your own weather by uploading a CSV file of time series. You can have 20 years, 30 years, whatever, how much ever the data that you have, or you can rely on our internal integration with NSRDB to get the historical time series weather. All the design details, such as the latitude, longitude, and such, the project lifetime, they all come from PlantPredict into PowerUQ. The sizing, which determines the POI capacity, number of modules, axis tilt, azimuth, all of this stuff also comes from PlantPredict into PowerUQ to establish a baseline of design. The uncertainty inputs start with these sections. So we have uncertainty assumptions that get applied on the nominals on the DC side, the AC side, a few system rates such as availability and curtailment, and the environmental uncertainty was GHI and soiling and such. So within the DC side, let's take a look at this particular module that we selected. This is the Trina 645 watt module. The nominal value is the most likely value. So this is the one that we get from the data sheets. And I think folks who have worked in PV industry are familiar with the plus minus 3% measurement uncertainty. So this is the smallest value it could be on the left, and then this is the largest value it could be on the right. That's how we capture the bounded uncertainty input for this specific field. Similarly, we can capture the binning effect of that was chosen for your specific site or specific installation, the temperature coefficient, degradation. Specifically, the degradation has a very specific and high impact on generation. So you can see the values here, the defaults that we provide come from studies from NREL and DNDGL. Heat balance thermal model coefficients such as UC and UV. We've given currently the nominal value here came from PlantPredict, where the assumption was made that UC is 29 and UV was 0. There are a few studies that show that from real life data, these numbers may not be 0, especially for UV. So you can test your hypothesis on how much impact this has on the outputs, generation outputs, as a result of the choices that you make. The next section has the uncertainty in inverter efficiencies. Then we have uncertainties in system derates such as availability loss. So just for simplification, I've zeroed them out, but you can enter values either from your own portfolio for the first year and the rest of the project life. We've made it asymmetric like that because typically first year demonstrates a higher availability loss due to infant mortality of components and such. And then the rest of the project lifetime, you have a similar availability loss assumption with uncertainty in it. For curtailment, again, I've zeroed it out for simplification, but you can gather the monthly values with uncertainty in them, specifically from, we've done a study on CAISO because this particular project was in CAISO, and the historical uncertainty in the curtailment was about 5%, but the net effect of that on the outputs as a result of its interaction with the rest of the uncertain inputs ended up creating a 10% systematic bias in the P50. So it's definitely something worth considering if you are not already considering in your simulations. In the environmental section, we have uncertainties in GHI, so that's irradiance, and folks might be familiar with the metation campaigns and how we can use to reduce the bias in this particular assumption. It's important to note that only the bias can be tuned. The uncertainty in that bias still might be there. So as a result of your MCP tuning, you can actually introduce and study the effect of how much that uncertainty in GHI also reduces with PowerUQ. There are a few other inputs that I'm not gonna spend a lot of time on, but one important one would be soiling. You can get your monthly soiling losses along with the soiling loss uncertainty, soiling loss model uncertainty. Finally, we have a quick summary of what design was captured from PlantPredict. So we have the DC-AC capacities, the DC-AC ratio, DC to POI ratio, and the specific weather that was chosen for running these simulations, and some metrics that point towards how much mean and spread of that weather was. So this is the interannual variability of GHI, 0.94%. Being in SoCal, it's very low, as you would expect. The next step is to hit simulate here. To save time, I'm gonna just go to one that I have already done. Here, our journey really starts with the conventional way of looking at a P50. And this might be a line that many of us are familiar with. This is how the pro formas in the industry currently look like. You take your first year energy and then degrade it over the project's lifetime with your choice of degradation coefficient. And you do the same for the P90. You take a haircut doing root sum squares of uncertainties, and the P90 from the first year gets degraded over the project's lifetime. The insight that PowerUQ provides here is that P50 is uncertain. And you can see the code of uncertainties as a result of all the uncertain inputs that we just looked at evolve as the project years roll by. So in the earlier years, you have lesser uncertainty, and in the later years, you can start seeing how the uncertainty impact increases. We give a few metrics to compare these. The first one being just the mean uncertainty. So this is the case that gives you the mean P50. What we really mean by that is the P50 is uncertain, and we're giving you the the mean metric of that uncertainty. And this triangle here that's formed as a result of the conventional assumption about P50 and the mean PowerUQ P50 is really the P50 bias in your specific project compared to how things have been done. We also give you a calculation of that for ease so that you can iterate over your design assumptions and uncertainty assumptions. In this particular case, it was about 4.7%, 4.5%, 5% for this particular location. Moving on to the downside cases. So the P90, as we saw, is derived from P50 for the conventional methods. But for PowerUQ, there is a uncertainty envelope of its own. So P90 has its own uncertainty envelope as a result of the downside calculations. And we give you two metrics. So first one being the mean of this uncertainty cone, which gives you the weather downside. So this is assuming that the model uncertainty had no impact or it was average. And this is the mean minus one standard deviation, giving you a more conservative estimate of downside. And this is something that's kind of more equivalent to how things have been done in the root sum squares method for uncertainty calculation. Using that, you'll see that the worst case annual P90 to P50 ratio, the risk ratio, is calculated here in the energy summary metrics. That's something that you can use for debt sizing purposes. We also give you the time series of all of these calculations here in a table that you can post-process for financial modeling or such. The next step here is to download all of these. So we provide you a configuration file that you can use to recreate these results, a table of all the P50 and P90 results, and also a uncertainty report that I'm gonna share now. The uncertainty report starts with a traceable and a traceable fingerprinted, digital fingerprinted report with timestamps and such, so you can use it for auditing purposes. It starts with definitions of the metrics that are provided as a result of these analyses, little bit of context information about the project itself, what the metadata is for that specific project, the assumptions about the design, and finally, the metrics of interest. So the first part being the weather metrics that give you a quick glimpse of what kind of weather was used here. So this was what was the source of the weather, what was the P50 of the weather, what was the spread in the weather, the interannual variability, and finally, a table that gives you a summary of all the uncertainties that were calculated as a result of the PowerUQ analysis. Starting with at the beginning of the model chain, the resource variability. So this is where the sort of weather impact starts. And you can see in year one is about 1.14%. As a result of this resource variability, you get variability in generation. That's a little higher than that. It's about 3%. The effect of all the model uncertainties together, it's about 4.8% here. And the net or total generation uncertainty as a result of both the generation variability and the model uncertainty, which is about 5.7%. Another metric of interest for folks usually is the 10-year average, just to get a quick glance at how much the project risk is. You can see that the resource variability averages out. So it goes from 1.14% to 0.36% over 10 years period. So does the generation variability from 3% to 0.6%. But the important thing to note here is the model uncertainty actually goes up a little bit. And this is because the degradation and mismatch loss due to degradation increases as time goes by. And that's why you see an increase in this particular parameter. So as a result, the net combination of the variability and model uncertainty gives you a slightly lower than this first year uncertainty, but it's still pretty high as compared to what the conventional methods would have yielded. The summary metrics provide you the P50 bias as we calculated, as we saw in the plots, the 4.7% for this particular project, and the extreme risk ratio. So this is the the highest sort of extreme downside case for that project. So if you are really trying to do the debt sizing for the project, this would be a number that you would consider to know how much risk that particular project is carrying from a generation perspective. Going back to the tool here real quick, we understand that some of these are new ways of doing things for the industry. So we've provided some tools to build a bridge to the conventional method. So the first one is for the inputs. This gives you a bridge to convert your normal standard deviation sort of inputs into the PowerUQ inputs because we use bounded triangular inputs. So here, let's say I assume that the degradation had 0.5% nominal value and 1% relative standard deviation. So that kind of preserves the power expected density of these two distributions and gives you the PowerUQ inputs to use, so which come out to 0.5% nominal with plus minus 2.5% as the min and the max to be used in PowerUQ. The second tool that we have provided here is the calculation of total generation uncertainty, which we saw in the report as well, as a combination of weather variability and model uncertainty as we calculated. And you can interact with this tool to calculate your P90 to P50 risk ratio for both the weather downside and the weather plus model downside in here. So here I'm showing the P90, but I can easily change this to P99 and see how that risk ratio gets more aggressive as we change those inputs. So let's return to Isaac for the next poll, and then we will dive into the next part of the results.
Okay, here's our next poll. This will be the last one that we show. I'll go ahead and launch this. What would you desire the most from an uncertainty analysis tool? All the answers come in. I see they're coming in now. Give you guys a few more seconds. All right, I'll end the poll and share the results. It's like measured data comparison for model validation / tuning would be coming out in the lead there. And now I'll hand it back over to Chetan to talk about the financial impact.
Thanks, Isaac. Let's go to the next slide. This is the same project that we looked at in our demo. What I'm going to do now is share the estimated financial impact. This is a 100 record project, single axis tracker in SoCal, where the lifetime P50 generation bias, as we calculated, was about 5%. Next slide. The simple assumptions that we made here for assessing the financial impact is a 20-year PPA with kind of standard assumptions about 70% debt and so on and so forth. And to compare all these scenarios, we kind of kept everything the same. So the PPA rate is the same. I know that in real life that's not going to be the case, but we wanted a kind of same stage to compare apples to apples. The first result here is the conventional P50 kind of gives you a result that has 104 bips or 1% lower realized IRR as the PowerUQ P50 assesses the impact of the 5% P50 bias. If you include the one standard deviation of model downside, which is this result here, the PowerUQ P50 with 1 sigma model downside, that gets to about 4% lower IRR. Obviously, this is kind of an extreme case. I mean, at that point, you would kind of assume that your model is broken and you should probably invest in or investigate why that is happening. The third result here is a kind of illustration of how PowerUQ distinguishes between weather downside and model downside. So let's say if you're extremely unlucky and all you get for 20-year PPA is P90 weather. So this is the net drawdown, which is about 2%. It's irreducible risk, but the good news is that it is a risk that averages out. So it spreads over the project's life. If you own the project for a long time, then this particular risk should average out. And just to note that we are not speaking of catastrophic weather downside here, such as hail or flood or wildfires. This is more specific to generation uncertainty or generation risk. Next slide, please. Specifically for lenders, the P90 to P50 ratio or the risk ratio is of importance as it determines the project's ability to pay its debts. On the left, we have a plot of how the weather variability averages out. So year one, highest weather variability, 2.99%. Then 10-year average is obviously 1% here, much lower. 20-year, even lower. So what this is really telling us is that the variability averages out, the model uncertainty does not. And you can see the effect of that in the risk ratios here. On the right, we are looking at now the P90 P50 ratios. The first year, both the conventional and PowerUQ, they kind of have the same results because they're assuming the same inputs for uncertainty. But the 10-year average is where you can start seeing the effect of weather averaging. The conventional results yield a slightly higher risk ratio, and PowerUQ is still a little lower than that. But the project term or the worst case is where you see the most drastic effect of the impact of model uncertainty that is not typically accounted for in the conventional methods. So this is where we see that the model uncertainties interact and compound, as we saw in the cone of uncertainties during the demo, are not accounted for in the conventional methods, and that's why we see this difference of 0.93 versus 0.76. Next slide, please. Let's so what does that mean for a real project, right? So all of the stuff that we've been talking about so far was theoretical. These were case studies of hypothetical projects. We went ahead and started applying PowerUQ to real projects. So let's take a look at one of the projects that we applied PowerUQ on. So this is a 3 or 4 megawatt project in Pennsylvania. So Pennsylvania, hence it is higher IIV, about 3.8%. And what the green line here in this plot, which was not there during the demo, is the measurement. So this is the actual measured generation as it happened over the 16 years. We just had some basic design inputs available to us to capture it in PowerUQ and run simulations. So as a result, we assume that our model was highly uncertain, and that is something that we can do in PowerUQ. If you do not have a very precise, high-fidelity model available, then you can just assume that your model has higher uncertainty to kind of account for that. The results show that PowerUQ was able to tune the actual P50 here. So you're seeing about 8 out of 16 years with PowerUQ. And the conventional methods only pick 1 out of the 16 years in this particular case, as it was captured in the details that were available to us. Similarly for P90, about 14 out of 16 years for PowerUQ, so which is roughly 90%, and 9 out of 16 for P90, which is again not quite the textbook definition of P90. One very important point that I want to stress here is that PowerUQ is using only the historical weather. This is not a weather-adjusted tuning. I mean, you can say that we are playing this game without any cheat codes. Next slide. Before I move on to the sort of grand finale of validation, I want to define our validation metric because it differs slightly from the industry convention. And we had to do that because, again, we are using historical weather and not weather as happened. So the performance index star, or PI star, is essentially measured over expected, except that the expected value here is it's not using the weather as happened, but the historical weather. So this is kind of us putting ourselves at the start line of a project building, just like you would be while you're building a new greenfield project. Next slide. So comparing the performance index as calculated using conventional method and the PowerUQ method. Here, over the project's lifetime, we see about 7% P50 bias or 7% over prediction on average. And you can see that it kind of increases over time. This is due to the compounding model uncertainties as the years roll by. Next slide, please. So the next step was naturally to expand this validation to more projects. So we looked at about 6 projects across the US in varying climates: California, Colorado, Pennsylvania, New Jersey. In total, 67 project years in all of those. And because we are doing comparison using performance index, you can kind of assume that every year is kind of independent there in the comparisons. The distributions on the right here show the spread of the project year performance index for both the conventional method, which is in the orange distribution here, and the PowerUQ distributions, which is in the blue here. While PowerUQ distribution is in blue, that's centered around 1, the conventional is on average 5% lower, revealing the P50 bias of about 5%. We are going to present a little bit of a deeper dive into this at PVPMC later this year, so we are really hoping to see you there. Next slide. So who are we? Who is PowerUQ? I am Chetan. I have been in renewables for over 18 years now, building data science products at companies such as SunPower, dealing with the realities of messy performance data. Mark, our CTO and co-founder, brings deep uncertainty research background with postdocs at NREL and NIST, specifically on uncertainty in PV module measurements, and is probably one of the best software engineers in the industry. We are also working with the PVPMC community on an uncertainty quantification guide. If you would like to contribute, please ping me. I'm happy to add you to the mix. Would appreciate your inputs. Next slide. So how to get started? First option is that we will be sending out a post-webinar survey. So mention your interest and we'll get in touch. Second option, send an email to support@plantpredict.com requesting a trial. Either way, the more you can share about your use case and yourselves, it will help us with the prioritization. Thanks. Handing off back to you, David.
Thank you, Chad, and well done. All right, on this slide, you're going to see our product pricing table. This is the PlantPredict product pricing table, and you'll notice that PowerUQ is added to that table. Earlier, I mentioned that PlantPredict subscriptions start for as little as $150 a month. We also offer annual prepay plans that save you a little money. You get basically 2 months free when you sign up for an annual plan. So we're bundling PowerUQ subscriptions into PlantPredict purchases for $15,000 per year, and that will come with up to 3 users. All you need to do is let us know when that you're interested in PowerUQ when we're writing up a proposal. If you currently are on a PlantPredict annual subscription, we can add PowerUQ to that subscription by prorating the cost based upon the number of months you have remaining in your current subscription year. So if you have 6 months remaining on your PlantPredict subscription, the prorated cost of PowerUQ will be $7,500, and that will give you access to PowerUQ for the remainder of your subscription year. All right. Before we wrap up, I want to mention one more thing. We're offering a small number of early adopter spots for PowerUQ integration at a significantly reduced subscription price. If that's something that interests you, now is the time to raise your hand. In exchange, we ask for 3 things: participation in a joint case study, a testimonial, and some data sharing to help us validate and improve the product. We make that process as straightforward as possible, and it's not really a heavy lift. What you get in return is meaningful. You get substantial savings on your PowerUQ subscription, full access to the integrated workflow that you've seen today, a direct line into how this product evolves, and a genuine first mover advantage of having a bankable energy model built on PlantPredict and uncertainty quantified in this revolutionary way while the rest of the industry is still catching up. These spots are limited and they will fill up. Mention your interest in the chat now or say something in the post-webinar survey or reach out directly over the next few weeks. We'd love to talk through what participation looks like for your organization. And we expect these spots to fill up probably by early summer, if not by PVPMC. So you really got to move quick on this. All right. And that is the end of our presentation. We are now going to move on into Q&A. So Isaac, if you would like, go ahead and serve up the first question.
Sure. So first question here would be, how are metrics assumed to be distributed around their nominal values?
That's a great question. The metrics are assumed to be distributed in a triangular distribution in our PowerUQ interface. You can obviously approximate any sort of distribution with a triangular distribution, and that's what I was showing in the tools section. That as long as you match the power spectral density, the result of that on your output is pretty much the same.
All right. And for our next question, in your P90 models, what satellite databases do you use as primary sources? And what track record or performance history do those sources have? Additionally, do you work directly with Solar GIS or any other similar solar irradiation data provider?
Yeah, that's a great question. Currently, we are using NSRDB, and as far as my knowledge goes, all the weather providers use similar satellite databases underlying. We have the ability to upload any historical weather from any weather provider, so Solar GIS, Solar Anywhere, so on and so forth. And we have had conversations with all of them to kind of get to a more tighter integration. So stay tuned on some of those details. Thanks.
Okay, and for our next question, which parameters do you find introduce the most uncertainty in P50 bias?
This is, it feels like the P50 bias is really, really sensitive to the two things. So first is degradation uncertainty. And the second one is the irradiance, the GHI. So if you kind of get these two, and there have been obviously efforts in the industry to kind of tune the uncertainty in these two by doing met session campaigns and the vast campaigns of degradation studies that NREL and DNVGL have undertaken. So if you kind of get those two right, then you kind of probably win half of the battle right there.
Okay, and our next question would be, what is the comparison in PlantPredict of NSRDB to other MET providers and the risk with NREL changing to LOTR?
I am not sure what LOTR stands for. Is it Lord of the Rings? I'm going to assume that the question is about how the NSRDB compares with other MET providers. At the end of the day, all of these resource data sets are based on the same underlying satellite data. So the good thing there is that they all provide the same or similar variability as a result of that. The efficacy of translating those satellite images into the solar resource is what the value proposition of these data providers is. So they may all have their own secret sauce that obviously we are impervious to, but we can work with any weather provider and their resource estimates with PowerUQ.
Okay. And another question here. So your guess here is that conventional methods are under predicting output by 5%?
That is correct.
Okay. And let's go to another question. Do you support working with TMY files?
We do support working with TMY files. It is not something that we would recommend because TMY files are a point estimate. They are a nominal input, just like how we saw the various inputs in PowerUQ. TMY files are a point estimate of essentially what the weather is for a specific location. So the way to use TMY files is still to have TMY files to create the first kind of reference calculation, if that's the constraint that you're working with, and then depend on the historical time series weather for the variability, because the variability is not just an important factor, but variability sometimes is also asymmetric, and that is a nuance that's lost when you use TMY files. Thanks.
Okay, and another question here. How does PowerUQ combine the different uncertainty components, and how does PowerUQ estimate the impact of various components on the annual net generation?
Yeah, I think you're asking for the secret sauce, but in a very high level, what I can say is PowerUQ underlying calculations are essentially Monte Carlo simulations. We combine the effect of weather variability with model uncertainties based on the inputs that the user provides and based on the weather resource that we get from if you're using the API, then NSRDB. If you're uploading your own historical time series, then that. So the combination of those two essentially give you the impact of various components. And you can do sensitivity analysis, either manual or automated, which is where we are working towards. That's on the roadmap, to give you tools to kind of have a uncertainty waterfall of various inputs and see which input contributes to how much deflection in the output.
Okay, another question. What kind of distributions do you support?
So currently we are using triangular distributions for inputs, which can be used to approximate most distributions that are useful in this particular context. We recognize the fact that if you are doing risk analysis for, say, extreme weather events such as hail or flood or any of those, then you would probably want to, or even equipment failures, then you would probably want to look into something like log normal or variable distributions. But that's really not something that we're focused on right now. So currently we use triangular distributions.
All right, Isaac, I think we're out of time at this point. So why don't you ask one more question and then we'll wrap it up.
Sure. So this will be the last one. Can I upload pan/OND files directly?
We currently do not support direct upload of pan and OND files, but the great news is that PlantPredict is about to start letting users upload their PVSys designs and PVSys pan and OND files. So once that integration is...
We already do support pan.
There you go.
Yeah, so pan and OND. We support already pan, OND, as well as SHD, and then PVC. So we offer those as options. We're just now building the capability to import the actual project file itself to build up the power plant. So,
yeah, so there you go. So once you get your project into PlantPredict, then getting that into PowerUQ is a breeze, as you saw in the demo.
All right. Well, thank you, Chetan, for taking the time to join us today and for the collaboration we've had over, it seems like a few years now, working towards this moment. So we're really excited about the integration and the partnership. So thank you everyone for joining the webinar today. You taking the time to hear this important message was really, really appreciated. We will be sharing this recording. So everybody that registered is going to get this recording, so you can look forward to getting that. We'll also go through all the questions that were submitted that we were not able to get to, and we'll respond back to your questions. Make sure to fill out the post-event survey. That's really important. We want to get your feedback on this topic. And also, we would love to get a few of you onto this early adopters program. Like I said, the spots are limited. Like, we have very few spots. However, these early adopters are going to be critical as we refine this product and start building it forward. And getting in early, I think, is really important and a really valuable thing for you to do. So with that, we'll close out, and thank you all for joining.
Thank you so much, folks. Thanks, David. Thanks,
everyone.
Isaac.
Have a great day.